Hey everyone, welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel. So we're going to be working with this problem shown on the screen, and this is an equilibrium problem, so let's go over it. So two forces of magnitude TA, which is 5,000 newtons, and TB, which is 2,500 newtons, are applied as shown to the connection shown above. Knowing that the connection is in equilibrium, determine the magnitudes of the forces TC and TD. All right. So first thing you want to do with equilibrium problems, just to make your life easier, is to draw a free body diagram. So this will consist of an X and Y coordinate system here. And we're going to make the origin point for our free body diagram this point right here where all these forces collide. And with our coordinate system drawn, now we're going to put on our known and unknown forces. So right here we have TA, which is supposed to be directly along the X, is equal to 5 kilonewtons, which is just 5,000 newtons. And then we have TB, which is coming over here from the side. Let's rewrite that TA in a different spot. So let's put TA down here, is equal to 5 kilonewtons. And then we have TB coming down in this direction. And TB is 2.5 kilonewtons of force. And it is 30 degrees off of that y-axis. And then we have, nope, wrong way. Then we have TC, which is one of our unknowns, is going in the up direction along the y-axis. And then lastly, we have our TD, which is also unknown. And that is going to the right along the x-axis. There we go. All right, so that is our completed free body diagram. We have all our forces known and unknown applied, and we have all their orientations applied. So next thing you want to do with equilibrium problems after you get your free body diagram done, and if you don't know what your next step is, always go with summing forces in the x or summing forces in the y direction, because these are your summation equilibrium equations where all the forces in those two directions must cancel with each other to be zero. So if you're not sure what to do next, always go straight to those equilibrium equations, and then you can see what you can find using those equations. So let's go ahead and let's just start with the y first. And it does not matter if you start with the x or y. Sometimes one is easier than the other, but in the end, you'll get the same answer. So I'm going to take all my forces in the upward direction as positive. Everything in the downward direction in the y will be negative, and they will all have to counteract each other to be zero. So T sub A, 100% in the x direction. Don't include it in the y. T sub B is in between the x and y, so it will have a x component and a y component. Well, T sub B is going down and to the right, so its components will be down in the y direction and to the right for the x, because they have to match that general arrow direction of down and to the right, so this has to be down and to the right. So for TB, since it's going downward, it will be a minus 2.5 kilonewtons times the cosine of 30. The cosine of 30 will make this 2.5 kilonewtons into the y direction for its y component. And it is cosine because the angle is off of the y. The angle is adjacent to the y-axis, and cosine is adjacent. And then lastly, we have TC. TC is going upward, so that is a positive TC. We don't know what that is yet. And then not including TD because, once again, it is in the x-axis. So that's all we have for the y. And T sub C is the only unknown in this equation, so we can easily solve for it. It is essentially just 2.5 kilonewtons times the cosine of 30. And that gives me 2.17 kilonewtons of force in the upward direction. So there is one of my unknowns already solved for. And we only need one more to go, which is the TD. Well, we can find TD by summing forces in the x direction because we've already done the y. So let's go ahead and do the x and we can get TD because it is in the x. So I'm going to take everything to the right as positive, everything to the left as negative for my x direction. I have TA here, which is going left, so it'll be minus 5 kilonewtons. TB's component in the x direction will be going to the right, so that will be positive TB, which is 2.5 kilonewtons. And this time, because the angle's off the y, I'm looking for the x. That angle's opposite of the x, and that will be sine, because sine is opposite. And then lastly, I have plus TD because it is going to the right. And that's all I have for the x. TD is the only unknown in there, so I can easily rearrange and solve for TD. So when I do this, TD is essentially 5 kilonewtons minus 2.5 kilonewtons times the sine of 30. And that gives me 3.75 kilonewtons of force to the right. So that was a very fast equilibrium problem. And the reason why it was so quick is because both of our unknowns, TC and TD, were 100% in one axis of the x and y. Equilibrium problems become a little bit more complex when you have your unknowns at angles. For instance, if we had something like that, if TD was like that, it would be a little bit harder, and even a little bit harder still if T sub C was also at an angle. But they weren't in this case. They are just solely in the y and the x, and it makes equilibrium problems so much faster to work when that happens. So I hope this video was helpful. And if you want to see more problems solved of this variety, please check out the other videos on our channel. Thank you for watching, and I hope you have a wonderful day.